Hi, everyone. My name's Chris. I'm a friend of science. And I usually start by saying, welcome to the NASA, but it's not NASA this time, it's ESA.
Simple.
He's from Europe.
No, I'm from an island just off the coast of Europe.
He's off an island off the coast of Europe. But he's with the European Space Agency, who notably landed on a comet, just a little thing. We talk about moonshots here at Google from time to time, and I always think the same thing. I'm like, okay, so you have a real thing like this, where you started it, you launched it 10 years ago, and you were working on it for many years before that.
Yep.
And it's an astonishing commitment, right, of time and resources, energy, and science, right? And have it all work is incredibly satisfying. And I saw in your bio that you're working on the James Webb.
Yep.
Which when I look at that, I think, how can this possibly work? Right?
We think that every day.
I mean, because it's such a complicated device, and the things we want it to do in space with its reconfigurability, and the thing that goes over here and the thing that goes over there. And I know I'm using lots of scientific terms here, and I apologize for that. And I think, but is it any less possible than what you did with Rosetta? So anyways, the long and short of it is, you're not here to see me talk, you're here to see Mark talk. So Dr. McCorcoran, do you want to come and take the stage?
Thanks very much. Thank you. We probably don't need this one, no. Yeah. So thank you, Chris, and thanks everybody for being here today. I understand the audience may be somewhat larger in the world beyond this room as well, which is good to know. And it's a privilege, actually, to be able to come and stand here after actually 30 years of work by thousands of people to get to this point. Last year was an absolute blast, an amazing thing to be involved with. And I specifically asked if I could come here. I'm in the neighborhood talking NASA Ames tomorrow, and I thought I'd come here because actually Google played a role, as you'll see later on. It played such a role in all of our lives, of course, but it played a specific role for us at the end of last year, which I'll come to later on. So what am I going to talk about? I'm going to talk about the Rosetta mission and its journey to this amazing object, which you see in the bottom here. You'll see much more of it, called 67P Churyumov-Gerasimenko. Comets are named for the people that discover them, so it's unfortunate that Bob Smith didn't discover this one. It's just a long name, but these two Ukrainian astronomers discovered it in 1969. Of course, comets are objects which are fascinating and have been fascinating for millennia throughout humankind. People have looked up in the sky and seen these strange visitors that would come seemingly out of nowhere, blaze across the sky for maybe days, weeks, in some cases months. And nobody had any idea what they were, where they came from. They were always thought to be these messengers from the gods, perhaps. This idea that these things came out of nowhere unpredictably might be portents of something bad that was about to happen. We see them as beautiful objects today. This is actually taken from the platform of the Very Large Telescope, which is an array of 4 8-meter diameter telescopes in Chile, where my colleague here in the front row, Hans Zinnecker, and I have spent many years using these telescopes to do astronomy. This is astronomy with the naked eye. You don't need an 8-meter telescope to see this particular comet, Comet McNaught. But as I said, it goes back thousands of years, and this is actually from 1066, or just after 1066. This is the famous Bayeux Tapestry, which was created by the Normans to commemorate the invasion of England in 1066. And this is usually the point where I point out this is the last time it happened, but other people have tried. And what you see at the top here is a comet emblazoned across the Bayeux Tapestry, and in Latin it says, "These men wonder at the star." People here are looking up, and they thought this was a portent of doom. And of course, for the English, it was. For King Harold here, it was a bit of a problem. For the Normans, it was a portent of good, you could argue. So, silver linings and all that. But what we now know from subsequent analyses of this particular object, and the fact that in the record over 1,000 years, this object appears to have come back every 76 years. So Edmund Halley, and you'll guess what the name of this comet is now, found that there was an apparition on a regular basis of a comet, and he said, well, maybe it's the same one. And it was. It's Halley's Comet. It's what we know as Halley's Comet, and this was actually seen many, many times throughout history. This is just one of the occasions. The last time that it came past was 1986. And of course, 1986, we were deep into the space age, and it was possible to actually go there for the first time. And so the European Space Agency launched a mission called Giotto as part of an international fleet to go and encounter Halley. Now, Halley lives out deep in the solar system, way out beyond the giant planets. And it comes in every 76 years, accelerates towards the inner solar system, goes extremely fast through the middle and back out again. And so what we could do, what we were capable of doing in 1986, was effectively do what anybody in this room, and I can say that with absolute certainty, anybody in this room would have to do this if you wanted to have a conversation with Usain Bolt, okay, when he was running the 100 meters. None of you in this room would be able to run as fast as him, right? So the only way you could do it is actually stand out in front of him as he sprinted past, and you'd have maybe a couple of milliseconds of conversation. Right? You could do that. You could just direct yourself to be in his path as long as you avoid hitting him. And that's what we did with Giotto in 1986. As Halley swung through the inner solar system, we were able to get Giotto to fly by at 68 kilometers a second. And we had just minutes of that encounter, the first time that a comet was seen close up, the comet nucleus. And unfortunately, it's a bit light in the room, so you can't quite see very well what's here. But this is the nucleus of Comet Halley, about 15 kilometers across. And what you see, and what was an interesting discovery at that point, is that comets are actually very dark objects. We think of comets as being composed of ice and dust, and therefore kind of the phrase is often used, dirty snowballs, and so you'd expect them to be highly reflective. Turns out they're not. They're incredibly dark. And the surface here is a mixture of dust, which has been lifted up from the comet as the comet heats up when it gets close to the sun. Some of that dust falls back down onto the surface, and slowly you get snowdrifts, if you like, of dust on the surface. And also there's organic material in comets. So there's actually complex carbon-bearing molecules in comets, and that makes it dark as well. Now, we've had a series of comet missions. NASA has been to several comets, and one of the most famous encounters actually did do what you shouldn't do, which is it did stand right in front of Usain Bolt. In 2005, the so-called Deep Impact mission, you can tell what's coming next, where it was two spacecraft together, and the front spacecraft was actually set on a direct collision course with the comet, Comet Tempel 1 here, and then the second spacecraft took pictures of that as the first one impacted. And that's the outcome. It turns out that's actually a very small crater. Another mission has gone back to Tempel 1 since and seen the crater left in a brief flyby. It's a pretty small crater, but a lot of material was lifted up. But why would you want to do this? What's the point? I mean, it's just not fireworks. It's cool, but what's the reason? The reason is that the surface of comets is, because of this dust covering and these carbon-bearing molecules, is not really the primordial material anymore. It's been processed. Every time a comet's come through the inner solar system, it's been frazzled, fried. Think of it as a baked Alaska. The outer surface is not representative of what's on the inside. And by excavating material from underneath and analyzing that brief flash of light from the material as it's thrown up, not only locally, but the Hubble Space Telescope was used to take data on this comet during this impact, you can try to understand what the comet's made of in the inside. And why is that relevant? Well, it's because comets are leftover material from the birth of our solar system 4.6 billion years ago. We have this kind of overview here of the cycle of life of stars and planets, which starts with very high-mass stars generating the heavy elements in their cores through nuclear fusion, through supernovae returning that material to the interstellar medium. That kind of mills around in a galaxy for millions or hundreds of millions of years, but then slowly gets reincorporated into dust clouds, which can then collapse down to form new stars. Those stars form in swirling disks, and around those stars you have protoplanets. They form as well. You get planets like us, but you still get a lot of leftover material. The asteroids and the comets and lots of small dust particles as well are leftover stuff. And that's important because some of that leftover stuff may have played a key role in us on this planet today. One of the models for the way the Earth formed is that it was extremely hot when it was young, and so hot on the surface it couldn't retain any water. So one of the big questions is where does the water come from that we drink and that we're made of, and all the water on the planet? If it wasn't on the surface shortly after the birth of the solar system, was it delivered from somewhere else later on? And comets could be a very important vector for that because they lock up ice and dust in the outer solar system, and those objects can then come into the inner solar system through perturbations and impact on the planets. You need about 100 million comets to get the water we have on the Earth. That sounds like a lot of impacts, but over 500 million years in the early solar system, that's not so often. Okay, there were lots of comets around. So investigating comets to try to understand whether the water in comets is the same as the water we have on the Earth is a clue to our own origins in terms of water. But more than that, the complex molecules which are in comets also, we know that comets contain amino acids, for example. Interstellar space is rich in carbon-bearing molecules. And maybe, again, because the Earth was hot when it was young, maybe the comets brought that organic material to the Earth, not life, but organic material, which could then be the building blocks of life. So we could, in some ways, literally be comet stuff. You've heard from Carl Sagan that we're star stuff, yes, but later in the circuit, we could actually be comet stuff as well. And so by going to a comet and investigating it in detail, not just a brief flyby, we may learn much more about our own origins. So I'm going to stop briefly here and show you a 5-minute film which we put together last year from a completely different perspective to try to open up this story about our own origins, where we came from, the role that comets might have played. And we did it, we wanted to reach the general public, so we did it through the medium of a science fiction film, which was novel. NASA called us up afterwards and said, how the hell did you do that? We want to do that too. Which doesn't often happen to us. It usually goes the other way around. So I'll show it to you, and it's something which is a word which I'm sure this company and many of the people I speak to are well aware of. The film is called Ambition.
Enough. Walk with me. Perhaps we should find you something a little less challenging.
I don't understand. I planned everything. Let me do it again.
Once upon a time.
Really?
This is a good one, I promise. What is the key to life on Earth?
Water.
Water. For a long time, the origins of water, and indeed life on our home planet, remained an absolute mystery. So we began searching for answers beyond Earth. Where could all this water have come from? In time, we turned to comets. 1 trillion celestial balls of ice, dust, complex molecules left over from the birth of our solar system, once thought of as messengers of doom and destruction, and yet so enchanting that we were to catch one. A staggeringly ambitious plan.
Are you talking about the Rosetta mission?
Throw me the probe. We harnessed whole planets and their gravity to chase down the comet. So many things could have gone wrong. A failure at launch, an error in the calculations, collisions, so many unknowns. With the technology we had back then, we may as well have been shooting from a slingshot. And tell me, what was it all for?
Knowledge.
Yes, but we also wanted to show what was possible.
this from the archives. There were bigger missions after.
Yes, it was the first one to catch a comet. Ambition. Stubbornness. Nothing has changed. We fall, we pick ourselves up again, and we adapt. I was watching you earlier. You actually did everything right. I destroyed your rock. I needed to see how you would react. You're ready. Reset. Nicely done. Let's begin.
So I'm sure many of you recognize Littlefinger from Game of Thrones there, Aidan Gillen, out there somewhere a million years from now looking back at our amazing mission. But of course we had to turn this science fiction, which we made last year, we had to turn it 30 years ago into science fact. So at the time of Halley, when we encountered with Giotto, we knew that we wanted to do more than just a brief flyby. We wanted to get close to a comet, rendezvous with one, and land on one, and follow it as it went around the inner part of the solar system to see it evolve, to see how the material flows from the surface and get exposure to the material from underneath. So in 1985, this mission was actually started to be planned, and by 1994, we'd got to the point where we were building it. It took about 10 years to build it, and just to give you a sense of scale, Rosetta, its wingspan from tip to tip is 32 meters. That's the size of an Airbus A320. It's got the biggest solar panels ever used on a spacecraft because, as you'll see in a moment, it had to go all the way out to the orbit of Jupiter. And out there, the sun is not very bright. Except, more importantly, it's cold. And having big solar panels to generate enough power for the spacecraft to operate, we had these huge arrays, which you see here folded up. And what you see alongside there in the middle is the spacecraft itself. It's about 3 by 3 meter cube, weighs about 3 tons. Half of that is propellant. And the rest is all the spacecraft bus and the electronics and the instruments, which I'll talk a little bit later on. And that's the famous Philae on the side, Philae the lander. It's about 1 meter by 1 meter. People say it's the size of a washing machine. I don't have a washing machine that big in my house. My boxer shorts would be cleaned much quicker if I did. But just to give you a sense of the scale of this, and it took till 1990, from 1994 or so to be built until 2003, and we were ready to launch in 2003. It was prepared for an Ariane 5 launch from Kourou in French Guiana, but unfortunately we had a failure of one of the Ariane 5s just beforehand, not the Rosetta launch. And then we had to have an accident investigation board, all the usual stuff you do. And by the time we were ready to go a year later, the comet we were going to had gone. We couldn't catch up with it. Okay. So within that 1 year, we had to pick a whole new comet to go to. And in 2004, in March, we were ready to go. And since I work in the space business, you can't have a talk without showing a launch. So this is the launch from French Guiana. So that's what we do in the space business. We build incredibly delicate scientific machines and then shake the crap out of them for 8 minutes, which is why it takes a long time to get these things fully tested. There's no going after them afterwards. So where were we going? We were going to this comet, 67P Churyumov-Gerasimenko. As I said, many comets are on elliptical orbits. 67P goes out beyond the orbit of Jupiter. It doesn't get super close to the sun at its closest point. It gets between the orbits of Earth and Mars. But the amount of solar flux that it gets by being that close is hugely more than it gets out in the outer solar system. So it changes its state an awful lot as it comes in. But as I said, in 1986, all we could do with our rockets was just fly past a comet. even now, we don't have big enough rockets to go to comets like this directly. We don't have enough power to get to one and rendezvous on this big elliptical orbit. So we have to cheat. And the way we do that, and you heard it in the Ambition film, is we harness the gravity of the planets. We actually use flybys. Oh, sorry. What we did was actually come back to the Earth 1 year later and use the Earth's gravitational power, energy, its force to slingshot us faster and onto a more elliptical orbit. We flew by Earth 3 times, and we actually encountered Mars once. This actually slowed us down a bit, but we used that to get us onto a more eccentric orbit. And since we were doing all of this, we flew through the asteroid belt twice, and while you're passing, you might as well make a visit, and we visited 2 asteroids on the way through as well. So this asteroid Steins in 2008, and you'll see when we get further out, we go to asteroid Lutetia. That's the comet going through. The comet is on a 6.5-year orbit. We didn't miss it. We just knew we had to wait for the next time around. So it was probably a bit galling to be on the spacecraft going, oh, no, next time. And so you see that we'll encounter Lutetia here in 2000, a little bit before that. And then we went into this thing called deep space hibernation. Even though we have these huge solar panels, we had enough power to run the spacecraft, but not if we had a problem. When we have problems on spacecraft, there's a lot of power used in what's called safe mode to sort of boot everything back up again. And so what we actually did was go into hibernation for 2.5 years. We shut the whole system down apart from some heaters to keep the fuel lines from freezing over. We turned off all the stabilization systems, and the only way we could keep the spacecraft pointed at the sun in a stable way was by spinning it. Okay, so we spun it up into a lazy spin, but the high gain antenna at that point is no longer pointing at Earth. It's pointing all over the place as it spins around. So we had no way of directly talking to the spacecraft anymore. The engineers hated this, as you can imagine, turning your billion-euro asset off out in space and waiting for the one thing that was powered up was an alarm clock. Okay? And that alarm clock was powered up for 2.5 years later for January 2014, January the 20th, and we had to hope that that was going to go off so that we could get to where we are here at the end of last year for rendezvous. And you can see we're trying to rendezvous quite far out in the solar system. We want to rendezvous while the comet's not active, far from the sun, and we want to get down to landing before it gets active. But we can't do it too soon because we need enough power to power the spacecraft up. So we had this 3-month window or so where we arrived and then had to do the landing. Incredibly, incredibly fast. Normally, you prepare for landings years in advance. You send another probe, you take pictures, you do analyses. We had none of that luxury. We had to do it in 3 months flat. On the way past, one of my favorite pictures, this is Antarctica on a flyby, skimming across the Earth's surface or above the atmosphere. We flew past Mars, and even though it wasn't yet probably in the Oxford English Dictionary, we took a selfie, because you do. I'm not really sure this is quite a selfie, because this is actually, Philae has an array of 7 cameras around the outside, and it took a picture of Rosetta, the spacecraft here, and the solar panel. And I suppose you call this photobombing by Mars in the background, So yeah, it was a very savvy mission even before we launched it. And here's our encounter with Lutetia in 2010, and it's kind of a bit jerky because we took lots of pictures and then we take fewer pictures until the encounter, and it looks like we got pretty close. Actually, we were 3,000 kilometers away at the time, so we have a good telephoto lens, let's put it that way. So this is a big object, more than 100 kilometers in size. So we get to after that, we turn the spacecraft off, spin it up, and pray. And here we are, January the 20th. We had a sweepstakes this day in the control room in Germany, in Darmstadt, and these are the guys, flight directors, who know this system inside out completely. And they had a sweepstakes, and it was 20 people in the room, 20 times. What minute is it going to wake up on? So when we got past the first minute, people went, hey, you lost. No, never mind, I get the money. And you go past the second person, oh, you lost. Person number 20, oh dear, it hadn't woken up. We were 18 minutes late, and we know why now in retrospect. There was a reboot on board. Perfectly feasible after that length of time, but unsuspected that it would happen. And we finally got the signals through both Goldstone and through Canberra, and we get the signals here, which you can see. That says we have a carrier signal, and predictably, we had some great enthusiasm. Because, of course, without this moment, without the spacecraft waking up, we had nothing. After 10 years of flight, There was no mission at all. So this was an enormous moment for these guys who worked for many years. I'll let you a little secret as well. On the day, we immediately had the spacecraft tweet, and for all the geeks in the audience, hello world, of course, exactly what you would tweet, right? And so we built Twitter into Rosetta years before Twitter even existed. Actually, this is Emily. This is our social media guru sitting in the front row here, and she tweeted. So social media has actually been a very important part of the mission for us, and we've had a lot of feedback. So yeah, it was hello world on that day in 20 languages. So. We soon knew after that we were heading towards a comet. You can see pictures taken from the spacecraft. You can see the tail developing of the comet here. It's actually a bit of a worry because this phase, as I said, we were further out in the solar system. We didn't expect activity at this point. We don't want activity at this point because we don't want to be next to an active comet when we're trying to learn how to land on it. Fortunately, this activity died away shortly afterwards. But that's the problem with comets. They're dynamic, living objects. It's not a dead body. And so learning to actually fly up next to this object and maneuver around it whilst it's changing has been a huge challenge. But beyond that, it was even challenging when we first got there because, if I remind you, this is Tempel 1. This is the object, this is the kind of prototypical comet that we thought we were flying to. Potato-shaped, fairly smooth, lots of smooth places to land on. And this is what the scientists were actually planning for. Now, when we started to get just barely resolved images of the comet, we began to see it jittering around, and you can decode a little bit about the shape from this. But of course, rapidly we got closer and we saw this. And this was something which this led to the moniker, the rubber duck, right? Which everybody said. And it was at this point, as you can see, a rotating image of this thing, that the engineers were just, oh, God. Because we actually have to fly next to this thing and land on it. The scientists thought this was fantastic, of course, because we may actually have two comets for the price of one. How do you get this binary object? Is it two comets, different origins, different compositions, which may have fused by a collision at some point? We still don't know that. We don't believe that's the case anymore. But again, engineers, scientists, right? The usual tension. And when we got close up on August the 6th in Rendezvous, it got even more, well, engineers and scientists, because this is the object we rendezvoused with. And it's just an astonishingly complicated object. It's 4 kilometers across. We now know the mass of this object, 10 billion tons. And you could quickly do the math there. You realize this object actually has density half that of water. It's much, much less dense than a regular iceberg. It would sit half the way up in the water if you could sit it in a lake. But it's the surface structures which have everybody amazed, because this comet actually has not been in the inner solar system for very many years. It was discovered in 1969, but we can track back its trajectory. We knew that in 1959, it had an encounter with Jupiter, which moved it closer in. Before that, it used to live further out in the solar system. So how come it's so eroded, so completely covered in all these craters and boulders? And one thing you need to know about the craters, these are not impact craters. This object's barely been hit by anything else. Those kind of collisions don't happen like they do in the asteroid belt in Star Wars, I'm afraid. Things are far apart. Collisions don't really happen like that between small bodies. These craters here are actually the water and the CO2, as it gets heated up from the ice phase, it sublimes into the gas phase from underneath and blows craters out from underneath. These are the kind of things we're going to be seeing in the next few months as these craters start erupting. This only happens when you're close to the sun, where there's enough energy and you get above the phase transition. So again, scientists absolutely thrilled by this, and the engineers looked at it and thought, well, the precision of our lander, the ability to deposit our object on the surface, it's not guided to the surface, it's thrown like a dart. We're going to land within a 1 kilometer circle. Show me somewhere flat over a 1 kilometer circle. And just to give you a sense of scale, and just to illustrate the glory that Google has brought to all of us in the world, is you want anything on the internet now, you Google something. I wanted a 4 kilometer tall object. This is Mont Blanc, just over 4 kilometers, as seen from 100 kilometers, which is the distance we rendezvoused at. This lady's sitting here in the Swiss Jura, exactly 100 kilometers away, looking at Mont Blanc. And just for scale, that's what it would look like if we put the comet into the picture. So it was called the Klingon ship at some point. You can kind of see bird of prey look here. And as we got closer, of course, we began to see these astonishing structures here. Cliff faces, areas that look like dunes, big boulders. But remember, none of this is rock. None of this is classical geology at all. It's much lighter. There is dust there. There are small particles, but these boulders are not great big rocks. They're matrix material of ice and dust. And the other thing to keep in mind is that all the other physical effects on the Earth don't really make a lot of sense. There's no atmosphere, there's no weathering, there's no rivers in that way. And one of the most fundamental things is when you look at an object like this, where is down? Okay, that boulder there, where's the down vector for that boulder? Okay? And of course, it's local. The down vector is local everywhere you are on an irregular object. You can try to pick out the area which has the biggest mass underneath you and say that's down, but you don't know the density profile well enough. This object is actually very porous on the inside. Not porous in the sense that there's huge caves, we don't think, but to get to the density we measure, it's a very loose structure. Gravity is not really acting on it in the way you would think of making a compactified object. So when you look around and you try to work out how things eroded to get where they are, you have to be very careful. You also have to remember that the comet's rotating every 12.5 hours, okay? And that centrifugal force changes things completely as well. And I'll show you that in a moment. Where you think the gravity would be highest, it isn't. And so there are areas like this as well, these sort of plains of material with kind of scalloping here. How did these boulders, for example, get there? You could think the other boulders might have fallen off cliffs and somehow slowly rolled down cliffs and landed in the valley. But how did these get here? Did they actually fall from somewhere, or are they actually material underneath which have been eroded out as the comet's been eroded away over these thousands of years that it's been relatively close to the sun? Are you exposing pieces of the matrix underneath? Okay. This one is christened Cheops for its pyramid-type structure. It's about 20 meters high, and I thought, well, you want to put this to scale, right? Everybody wants it to scale. So I made this image and instantly realized that we couldn't release it from the European Space Agency, because you could imagine what would happen if we did, thanks to you guys. Every lunatic in the world, sorry, but anybody watching would say, hey, look, told you, conspiracy, face on Mars. So this was released through a back door. It didn't have ESA's tag on it. I can now say that I did make it, but it's also illustrating the fact that we have this Egyptian naming theme. Rosetta, the mission, of course, refers to the Rosetta Stone, which is the way of decoding Egyptian hieroglyphics. And the naming scheme for the geological areas all actually have the names of Egyptian deities here. And this is what the scientists, of course, are doing now, is trying to characterize the various areas, try to understand how they would have evolved, because not all these areas see the same amount of sunlight all the time. I'm going to hand around a model of the comet here. This side area really hasn't seen much sunlight at all in the last 6 years or so, but as it moves towards the sun, it's going to be seeing more sunlight. So the place where you actually get more light, you get more activity, you get more sculpting. So we're trying to work out how these areas correspond to solar illumination and other things. This is an honesty test. If I don't get it back at the end, I'll be able to dine out on saying that it got lost at Google. And of course, one of the other pictures which has been shown many times, again, to give a sense of scale, which we like a lot, is this one, but I'll leave that one best unspoken, perhaps. It's not snow, unfortunately. And we've put a lot of our pictures in the public domain. We release our images from our navigation cameras, all released through Creative Commons. And we encourage people to go and do things with them. And in fact, there's many, many creative people out there in the world, many in this room as well. And this is just one thing that's been done by one of our friends, Matthias Malmer, making 3D models. Actually, he works in the video industry, knows how to do this stuff, took the images and created shape models. We're doing this scientifically as well. But I have to say, sometimes these guys are better than we are at it for good reasons. They do this as their daily life. But we didn't just go there, of course, just to take pictures. We went there to do science. So I'll just give you a brief rundown of kinds of scientific instruments we have. On Rosetta itself, which carries most of the scientific instrumentation, we have cameras which span from the millimeter end, we can actually see beneath the surface of the comet, all the way out to the UV, through the infrared and the optical, taking lots of images. We measure, as the material flows past Rosetta, we measure the gas and the dust through mass spectroscopy, see what it's actually made of. We know, for example, that the comet stinks. It's got a lot of organic molecules. It's got hydrogen sulfide, hydrogen cyanide. It's characterized as being a horse barn with the lovely addition of cyanide. So we've been thinking of making a bottle of perfume, actually. I just don't think it'll go down very well, but, smelling like a comet, it stinks. It's not nice. We also we capture individual particles of dust. We measure them with atomic force microscopes on board, and then we zap them with little high-powered LEDs or ion guns, rather, and then see what material comes off it so we can analyze what it's made of. There's a plasma associated with this comet. Even though it's very cold, well below freezing point of water, there is a plasma wrapped around it. Mostly it's the solar wind which is wrapped around it. Then Philae, the lander itself, is much smaller, has quite a complement of scientific instruments as well, though. So lots of images, you'll see some of those as we go down to the surface, and also microscopy of the surface. We analyze the material in situ now, and we try to tie together in the one location, or as it turns out, the multiple locations we landed, the material we see there with what we can see from orbit around the comet, so we can try to tie that together so we can get a more global picture. And we had a drill on board to actually go down 25 centimeters below the surface and pull material up and put it into a laboratory on board. Interesting experiment is actually linking the two spacecraft together through effectively FM frequency radio waves and doing tomography of the interior of the comet, which is kind of cool. And then the last thing we do is beam data back home, sensible thing to do. But we can actually measure the speed of the spacecraft to a precision of roughly 1/10 of a millimeter per second at that distance, which allows us then to measure the gravity and the higher order moments of gravity, what the internal density structure is. One of the most basic things about the comet, people always ask, why is it that you show these pictures which are snowy white when you tell us it's dark, and the one I'm carrying around is dark? Well, of course, we just crank the contrast up so you can see anything. But to give you a sense, Enceladus is one of the moons of Saturn. It's coated in fresh ice from the water which comes out through the stripes at the bottom there. Effectively reflects 100% of the light that falls on it. The Earth is relatively dark, only reflects about 30% of the light that falls on it. The moon, which we think of as being white, only reflects 12% of the sunlight that falls on it. It's a very dark object in reality. 67P, I promise you, is there. Reflects about 6% of the light that falls on it. It's just like being in a coal cellar. It's incredibly dark. People also ask us, why is it that you only show black and white pictures? Why won't you show a color one? Well, this is the right brightness, and I'm going to turn the brightness up and turn the color up, because it is that color. It is just incredibly dark and dusty. There is very little color differentiation there, as the human eye would see. But we have filters on our cameras which can enhance the colors a bit. And in fact, you do see some color differences. And you can see here the head part of the comet here compared to the neck. You'll see as I scroll down a bluer color in the neck. And we believe that that's because the dust coating there in that neck region is actually thinner, and we're seeing the ice coming through. It's more exposed there. Because ice, of course, we do expect to see ice. At the moment, we're seeing a very dusty object, but that dust will be blown away in the next few months as we have the whole fresh phase of heating. And then as we move back away from the sun, some of the dust in the atmosphere will fall back onto the surface and coat it again. And actually, that's what kills comets in the end. After thousands of years, you build up enough dust on the surface. You don't blow it away each time, all of it. You get an insulating layer. You can't even heat the ice anymore. So we know that in our solar system, there are many dormant comets, former comets. Comets don't live forever. So I taught you about the surface gravity and about centrifugal force. We've measured that. Here's the effective gravitational potential. You would think the gravitational force would be strongest when you're standing over the biggest piece of mass. So, but what we see here is because of the spinning, the gravitational potential is actually lowest on the two ends of the comet, okay? And you can also see that the local slope of the surface, let me finish this thought, the local slope changes a lot relative to the gravitational potential. You can see it can be up to 60 degrees off. So if sort of metaphorically, if you're walking around, suddenly gravity moves off by 30 degrees. It depends what's under the surface. It depends where you are.
Where's the rotation axis here?
The rotation axis is more or less through the neck. So if you were to take the comet, stick a pin through the neck, it's the two ends are spinning at the highest speed. Question?
Okay, yeah. So the dust, when it seems like if it was getting dormant, wouldn't you still have some of the dust kind of blowing off? I mean, it seems like you would I'm surprised that it would that you would have more and more accumulate.
So yeah, the question was, why is it that we don't blow the dust away every time? Why do we get an accumulating layer? Well, it's just the physics of the gas and the dust and how they couple. The gas can flow away very readily. It flows away at high speed. The dust is coupled to the gas at the beginning, but drag forces act on it, and it gets slowed down and falls back to the surface. So a fraction of the dust ends up back on the surface every time. And that is particularly bad when the velocities of the gas escaping are low, which happens when you're furthest away from the sun. So we get that coating. We know that the comet dust we're measuring today is old dust from last time around the sun, we believe. We're going to be seeing different kind of dust coming fresh from the surface now. So just to give you a sense of scale about the gravity, this is one of my favorite pictures, just showing kind of the sweeping vista on the comet. You know, this cliff here, this cliff face is 100 meters high from top to bottom. So I'm sure half of you in the room immediately thinking base jumping, right? It would be the most boring base jump in the world. Your parachute wouldn't work because there's no atmosphere, but you wouldn't need one, because it would take you 20 minutes to get from the top to the bottom. And you would arrive at the velocity of 0.2 meters per second at the bottom, 20 centimeters a second. You would just walk off the bottom. But actually, you'd have to be careful, because you know how base jumping is? To clear any obstructions, you stand at the top, as if I've done it, right? And you jump up and out. But if you jumped too hard, you will go to escape velocity. So I'm going to get you to demonstrate what escape velocity of the comet is. So if you all stand up, you're all going to jump off the comet. So if you all stand up, you have to jump that high. And if you can jump that high, 4 centimeters, you will have reached 0.9 meters a second. That's escape velocity for 67p. So 3, 2, 1, jump! Yay, good. Now, of course, I've talked about this comet, its gravity, its structures, and people are interested in that. But of course, one of the great things is it's changing. We're seeing activity. We're seeing material begin to flow away as we come in closer to the sun. And in fact, we look in some of these sublimation pits, these craters, if we crank up the contrast, we see stuff beginning to come out of the craters themselves, right? The material flowing away. This is what we would expect. And as we're getting closer to the sun now, we're seeing more and more of this activity. Here are some of the dust particles which we're gathering. They turn to be very clumpy fractal structures, which as soon as we catch them, they fall apart and just, they're not strong at all. Structure, yeah.
I have a question. With such a low gravity, how do you keep Rosetta
Yeah, it can be in orbit. When we arrived at 100 kilometers, we actually got to the point, we don't know how massive the comet is at that point, so we don't know how to go into orbit. You need to know that, right? That's a starting point. So we flew in triangles, in front, powered triangles. We would cruise, then power, go this way, go that way, and move closer until we started seeing bending in the trajectories, and that would tell us what the mass was. So when we get down to 30 kilometers or so, this is a several-week orbit, okay? But it's an orbit. So we were actually in orbit for a while. We're standing back now because the comet's getting active. So we're back out at 100 kilometers again. We're not in orbit there. We're flying trajectories. But down at 30 kilometers and below, we consider ourselves to be in orbit. So it's weak, but it's, gravity still works on those scales. And we've told you, we've measured the gravity, the plasma, the interaction between the comet and the solar wind. This is a very technical graph, but it's much easier if you listen to it. So this is speeded up to put it into audible frequencies. What you're actually hearing is the rotation of the comet modulating the interaction of the solar wind as it flows past. So the sound of a comet spinning in space, cool, right? Now, here's the kicker. I showed you the film Ambition at the beginning, and I talked about the fact we were trying to go and see whether the water on this comet was the same as the water we're made of. The way you would do that is to measure the deuterium to hydrogen ratio, the isotope of hydrogen, because on Earth it's one number. It's always the same everywhere, okay? The amount of deuterium in water. What we know from other comets is it tends to be high on comets, whereas asteroids are pretty good. Asteroids are quite Earth-like. A comet was measured in 2012, which was seen to have exactly the same ratio as the Earth. And it's from the same family as 67P. So we thought, wow, maybe these families of comets at this distance from the sun, maybe they have the right kind of water. Unfortunately, 67P has the worst ratio ever measured, very high. And so, of course, we already know that this comet didn't bring the Earth's water, sort of by definition, right? But what it opens up now is this question of trying to create a recipe for making the cake. You know, at what level? We know the Earth has been hit by comets. We know the Earth gets hit by asteroids. We know that there are all these objects out there. Some are closer to the sun, some are further away. But we're trying to build up the picture of how many of these versus how many of those could end up with the right kind of water that we have. You see, there are very few objects at all that have water with a lower D to H ratio than the Earth. So since we do get hit by some of these, how do you get a lower one on the Earth? Okay. And there are other models for how the Earth's water came as well, and other people will comment on that. We can ask some questions about that. Maybe it didn't get delivered from the outside at all. Maybe it was stored up in the Earth, even when it was very hot. One of the more fascinating things about the structure of the comet is this. You can see these lumps. They were originally called dinosaur eggs, goosebumps. They're about 1 meter or 2 across. And we've seen internal structure, so not on the surface, which has been processed, but in the pits, we see this texture. And the question is, are these actually the primordial structures, the objects which formed at the beginning of the solar system, excuse me, and they actually came together, agglomerated, and formed the bigger objects called comets? Are these the building blocks of comets we're actually seeing inside? We may get lucky, and we may see it much more clearly, because 67P has a 500-meter long crack running through the neck, which you can see here. We know comets fall apart. We see it all the time. 67P could fall apart this time around the sun. The engineers would hate that because they have to fly around 2 objects simultaneously. We would love it, right? Because then we could see the primordial material on the inside before it gets affected by the sun. There's no guarantee it'll happen this time. It'll happen in the future someday. This object's bound to fall apart. But it would be very cool. Yeah, well, yeah, thank you. There, so, all right, last bit of the talk, let me talk a bit about the landing. Okay, so here's another selfie again. This is real photobombing now. A comet in the background of your selfie. I mean, you can't do better than that, right? So we arrived in August, and we knew that we had to plan to get down to the surface by November before the comet got too active. And so we started identifying landing sites. None of them were going to be fully clear. We started with 10, A through J. We whittled it down to 5. And you can see, in each case, the square here is 1 kilometer. So this is the typical accuracy we thought we would have when we threw our dart at the comet, because we don't know the gravity that well, and the gravity is non-uniform. So landing in a certain place is not so easy. We ended up picking site J as the best of all worlds. We also had the place that had sunlight and satisfied other constraints. But you can see there are cliffs and there are structures here. It was not guaranteed at all that when we hit the surface here that we would be safe. And C was the backup over there. In a bit more detail, this is the landing site. Now as an error circle, 1 kilometer, we aim to land there. And the way to think about it, in fact, is like darts. If you, to scale, if you stood in front of a normal dartboard, the dartboard, at the distance of what's called in English the Oki, is exactly the size of the comet. Okay? It's the same ratio. The distance we threw from, 20 kilometers, and the size of the object. As you'll see in a moment, we landed in the 25. Okay? We were 120 meters away from the nominal touchdown point. Amazing. I mean, the guys that drive this spacecraft deserve huge credit to go 10 years through space and then throw the dart. They didn't get a bullseye, so they shouldn't get cocky, but they were pretty close. Now, okay, so how do you do this? Well, if you're an astronaut, it's really easy, right? You do this.
Got it. Admittedly, it's translating really slow, but at least we hit our comet.
So this is Alex Gerst on the ISS who did a demo, an educational demo for us. He spent hours doing this, throwing an ear plug at a piece of Velcro on a rotating sphere. It looks good in the video, he got it, but there's lots of the one where it pinged off it's all good. In reality, it was much more complicated than that, of course. We worked our way down into a 10-kilometer orbit, took high-res pictures. We then had to work our way back out to get up onto this trajectory. Then when we dropped down from 20 kilometers, more or less, straight towards the nucleus, we dropped Philae off, pushed it out of the back at 18 centimeters a second, and then Rosetta pulled up so that it could maintain radio contact throughout the entire 7-hour descent onto the surface. Okay. 7-8 hours descent. So we actually it was Isaac Newton at that point. It was all down to the laws of gravity, no guiding at all. We had a gyro on board, a big stabilization wheel to make sure we maintained orientation. And it looked roughly like this. Some music here composed for us by Vangelis, of all people. Nice and original music. Of course, the comet's rotating 12.5 hours, and it takes us 8 hours to get to the surface. So you're not aiming at the point, you don't even see it when you throw. Now, that was the plan. The plan being, of course, you're arriving at 1 meter a second. It's walking pace. It's a 100-kilo object. There's low gravity, but inertia is a killer, right? We hit hard, relatively. Try it. Somebody 100 kilos, let them walk into you at walking pace, right? You'll feel it. And, of course, the danger was that we would bounce. So we had ice screws in the feet. We had harpoons underneath. We'll get to that in a moment. So this is what it looked like in reality. This is the farewell shot. This is Philae taking a picture of Rosetta with a solar panel as it backs away. And this is the equivalent. This is Rosetta taking pictures of Philae as it descends away down to the surface, getting more and more pixelized as it gets further away, of course. We even see it moving across the surface of the comet. Series of pictures here taken a few minutes apart. You can see Philae in each case, the little legs descending above the surface. It's actually descending pretty much vertically, but because Rosetta's moving and the comet's rotating, it doesn't look like that, but it's more or less going straight down vertically. It's a picture taken from 3 kilometers as the lander's approaching the surface. And here are the pictures taken at the surface from about 40 meters down to about 10. You can see the lander leg here. So that's from about 10 meters. And to give you a sense of scale, this is from Philae, but if I put Philae in the shot and put it on the surface, this is what Philae would look like. So it's still pretty rough at that scale, right? It's not, it's not as smooth as we would like to have been. And this is accurately where we landed. This is the place we landed. And in fact, that boulder there could be part of the reason when we actually did bounce, as you know, we didn't bounce vertically, we went off at an angle, okay? And it could be in part because of hitting that rock. And so this is where we touched down. You can see the 3 feet, okay, there. So we have pictures from orbit. I can now play the sound of landing through transducers on the legs. And that's in real time. That's what landing was. We hit down, we went through about 25 centimeters of dust, which is what you see, these pools kicked up, and we hit a very rigid surface. Even though, again, we know that it's a very low density object, that doesn't stop it being pretty hard. Think of balsa wood or something. It can be very light, but can be fairly strong. What we then saw shortly afterwards was this from our navigation cameras. We see a dark patch there. That's a shadow of the dust kicked up by Philae being cast on the surface. And then we see Philae here and Philae's shadow. So we see Philae departing in the navigation camera images. And in the high-res pictures, this is the touchdown point. And there's Philae on its way. Philae flew for a further 2 hours and very luckily clipped a cliff on its way, because if it hadn't clipped that cliff, it would have gone back out into space again. So what we now know, we've reconstructed, is it flew for roughly an hour, hit the edge of a cliff here. During this phase, I told you it had a big stabilization wheel internally. That kept it level as it came down to the surface. Well, that was turned off as soon as we made first contact. But as we then flew again, the angular momentum transferred into the lander, and the lander started rotating, but level. So the lander started rotating. When it hit the cliff, it started tumbling. We never lost radio contact with the lander throughout, though, which was amazing. And then an hour later, we end up somewhere over here on the edge. This is landing site B, by the way, which we chose. We didn't want to land in, so we just flew over it instead. We ended up here. We bounced one more time, flew up a little bit, and then a few minutes later came down a few meters away. And here are the heights that we got to. We got about 100 meters, 150 meters above the surface during this flight. If we hadn't hit this cliff, the problem is this is actually stretched out linearly. The comet itself is curved. We possibly would have gone off into space there. But we did land, and we landed in this place, up against a wall. We think we're tilted up against this wall. It's relatively shadowed, so we don't actually have enough power on the lander to keep it going. What we wanted was to land in a sunny location where we'd have enough power to keep the lander, after its primary battery, 60 hours, ran out, the rechargeable batteries would kick in and keep us going. We didn't have enough sunlight in this location at this time to power the secondary battery, so we went into hibernation after 60 hours. The traditional question is, why don't you use nuclear power on your spacecraft? Because we're Europeans. But what's very fascinating about this is, I mean, if you want to have a silver lining, when we first landed, we landed on a pretty boring place covered in dust because that's the safest place we could land. The scientists didn't really, they knew they had to land there, but they didn't want to. They wanted to land up next to some primordial material. And that's where we ended up, right next to a cliff made out of ice and dust matrix.
This was all planned.
Of course. Absolutely. I only wish. We would have had a lot more sleep in the last 6 months. So, of course, at the time, you know, even touching down on the comet was a colossal success. Nobody had ever done this. First soft touchdown. At this moment, this photograph, the guys who are about here in the picture already knew we were flying. These guys didn't. So we, you know, big media success. It was a huge day, the 12th of November. Absolutely astonishing. I mean, the world really got into this. And we had, you know, front covers of newspapers absolutely everywhere. It was just astonishing. It became one of those things where people were talking about the fact people were talking about the fact people were talking about it happening, and it just absolutely amazing. So in fact, yes, we certainly didn't plan it, but if you want to have the maximum possible engagement from the public, build in a bit of jeopardy in your mission and make things not work properly. And we got to the end of the year, of course, and this is one of the reasons I'm very happy to be here today. We had a Google Doodle on the 12th, and then, without us knowing about it, on the end of the year. This one I found, I'm not sure I should really say this here, but you know, just an interesting lesson about a risk-averse company, let's put it that way. We knew that this Google Doodle was being made, the landing one, and on the 12th of November, I kind of thought, I went on Google, and it wasn't there, and oh, come on. So I sent an email saying, you know it's today, right? To which the reply was, yes, but we're not posting it until you land successfully. So, good enough, I think, right? Front cover of Science magazine, all letters going out of the UK had this congratulations to the European Space Agency, and as a Brit, the Brit saying anything positive about Europe is not very common, so thank you very much. And the flight director, Andrea Camazzo, one of the key people in the year here. This down here is actually is a Hollywood award, or Hollywood nomination for the Ambition film. So our friends from Poland who made the film for us had a nice evening out in Hollywood on the back of Ambition. And a couple of things, I got to show the competition first and then you, but the end of the year videos, this is Facebook.
The most powerful force on this planet is human cooperation.
Stop defining each other by what we are not, and start defining ourselves by who we are. We can all be freer.
And then yours starts, well, it's halfway through, of course, a little more bizarrely.
Did you hear those words?
Just rendezvousing with this comet is an extraordinary thing. We're going to make discoveries that no one's imagined yet.
So Bill Nye, the science guy, by the way. So just an amazing thing to be involved in, and it keeps on going. I'm going to show another 3-minute film to show another way we've engaged, and then I'll wind up at the end. It's a way we've engaged, and it happened by accident, but it worked extremely well, and we've made a series of films to engage with kids. And you now know a lot about the comet, and see how much of what I've told you actually appears in this summary. This is what happened on the 12th of November.
Over 10 years had passed since Rosetta and Philae launched on their exciting mission to Comet 67P Churyumov-Gerasimenko. After 3 months investigating the comet from orbit, it was time to send Philae to its surface. A long night of final preparations lay ahead of them. Finally, the moment everyone had been waiting for arrived. As the world held its breath, Rosetta moved into the exact position needed to make sure Philae would reach the landing site that scientists on Earth had picked earlier in the mission. Philae and Rosetta were sad to be going their separate ways, but excited at the same time, because this is what they had been waiting to do. Philae was away. It would take 7 hours to reach the surface, but Philae wanted to get started on his measurements right away. He could soon see the surface in incredible detail, and the moment he had been dreaming of had finally arrived. He had reached the surface of the comet. But all was not right. His harpoons did not fire. Philae realized he couldn't relax yet. He was rising from the surface again. Philae was scared he might drift off the comet completely. This was not in the plan. But eventually, he came back down again. However, as he looked around, he realized he had landed in a completely unexpected location. Philae immediately set to work on studying his new home. It took him just over 2 days to conduct all the experiments he had brought with him. After all his hard work, Philae began to feel tired, so he made sure to send all the data he had collected back to Rosetta. As the sun set over Philae's new home, he fell into a deep sleep, safe in the knowledge that he did his main job well, and that his family of comet-chasing heroes would be proud of his achievement. Who knows? Perhaps one day enough sunlight would fall on his new landing site and wake him up so that he could carry on investigating this incredible world. And so, as the comet moved over closer to the sun, Rosetta prepared for the next part of her exciting adventure.
So the big question is, where is Philae today? We actually don't know. It's up against the shaded region. We know pretty clearly where it is. It's flown over. You can actually see the 2 red dots. The first one in the top left corner is where we touched down. The second one is the cliff we hit. And we know we're roughly here. In fact, we've refined this a little bit better. We do this through the tomography ranging experiments with the comet. We know the timing very accurately. So we believe we're somewhere in this region. But you can see there are lots of little white dots everywhere. Okay? And we've been looking at all the images. Philae is roughly 1 or 2 pixels in size at the closest pictures we have. Incredibly difficult to actually sort out. We'll have a post out next week showing a little bit about that. Where we think we are, but we haven't definitively identified Philae. We're waiting for the sun to increase, because as we get closer to the sun, the energy increases. We may recharge Philae's batteries. It may come back to life this summer. We're listening out. We're hoping to hear from it. At the moment, we haven't. Just to show you, what we're really doing in studying the surface of the comet, this is an amazing image taken during a very close flyby on Valentine's Day. We flew 6 kilometers above the surface, and again, you see these incredible structures. And incredibly diverse terrain in terms of mesas and plateaus and dust and boulders. No, cracks up around the neck. So, but if you actually look in more detail, you get to see some very interesting things as we zoom in. And the highest res picture that we've released so far is actually taken just from about 8 kilometers above the surface. And this is with the sun right behind the back of the spacecraft. So you don't see many of the shadows. And in fact, what you do see is Rosetta. It's Rosetta's own shadow, okay, from 6 kilometers up. It's 8 kilometers up. And so we're in this position now where we're investigating things absolutely astonishing, sort of Chesley Bonstell alien landscape. I mean, this is kind of science fiction from the 1950s in terms of the pictures, and it really looks like this. But more importantly for us now is it's starting to look like this. Every day we take a picture of it, we're seeing more and more jet activity, more material flowing away. This is the material which then comes out tens of thousands of kilometers away, flows out into the tail, which you should then be able to see behind the comet. I hesitated there. We won't be able to see this comet naked eye from the Earth. It's never going to be bright enough. 25 centimeter telescope will do it, but you don't need that. We're there, right? We're actually there. And just one last picture before I finish. This is one we released last week. Over a space of 3 minutes, we saw a jet come out. 2 pictures, 3 minutes apart, and we see jet emission. So we're really in this fantastic phase now. We'd love for Philae to wake up, but you know what? It doesn't matter. We have Rosetta there doing amazing things. So let me wind up. We're at this point now where we're actually flying by. We're learning to live with this comet. The closest approach, what's called perihelion, is on the 13th of August. That's the date at which nothing really happens apart from the closest point to the sun. We are currently funded to the end of this year, but we think should be no problem continuing. We have enough resources to fuel on board to run until late next year. But as you think about it, we'll be coming out of the solar system again. So we have to choose. Do we go back into hibernation? Nobody likes that idea. So actually what we're currently investigating is whether we can land Rosetta on the surface and have it all over again. The only problem is, of course, we won't have another spacecraft to talk to. So once Rosetta hits the ground, it's over. But it'll be a fun day, I think. Lots of social media, all the good stuff there. And yeah, it's not over. And let me end by thanking you for letting me come and take your time today. Everybody else watching out there, thanks very much. But I'm just standing in front of a mission of thousands of people across Europe, across the world. The United States is involved, NASA's involved. A lot of people have become involved, making movies and all sorts of stuff, lots of big media, and my communications team who've done a lot of the stuff you've seen here. It made it just a privilege for me to be here today and say thank you very much and keep watching the mission. Thank you.
One question regarding the sunlight. So obviously it changes around, during orbits.
Rosetta flying around a comet.
No, the comet flying around the sun. But the intensity, you didn't comment on how would it feel for a human if you were standing there. Like how bright or dark would that be? Would it be like you're in the middle of the night, or?
Well, at its closest point.
What's the lumens like?
Well, at its closest point, it's between the Earth and Mars. So it's it's roughly like a sunny day, on the Earth, roughly speaking, because the atmosphere absorbs some light. I always make this joke that when we're out at Jupiter, we don't have enough power to run the solar panels and so on. Actually, at Jupiter, the sunlight intensity is roughly the same as a typical British summer day under cloud. But, so, we have an enormous dynamic range in sunlight on the Earth, right, whether it's cloudy or not. So, but it would be cold, of course, because you would be radiating to space. You've got a cold object next to you as well.
And one short one. Where does the outgassing start?
Well, we see it happening from many parts of the surface. We see it specifically in certain areas. We saw it actually already at 3 astronomical units. The astronomical unit is the distance between the Earth and the Sun, 150 million kilometers. We saw that initial outburst actually at more like 3.5 AU. So activity can happen at any time. It depends very much on a particular fortuitous orientation with respect to accumulated sunlight on a given day and maybe a pocket of volatiles near the surface expanding and blowing up. So activity, we've seen Halley, the activity continued a long way out after perihelion. So activity can happen, but it goes as the square roughly as the distance, or the inverse square with the sunlight. And there's also thresholds where volatiles reach certain temperatures and suddenly get busy. Yeah. So we're seeing a lot more activity now than at the beginning.
So does Philae have cameras that can point back out in space if it wakes up?
No, what it has on board is 7 cameras around the outside, of which 2 are a stereo pair, but they look horizontally. And then it has cameras pointing down. That having been said, we are tilted at an angle like this, and we know that we can see in space. We actually, when we did the first panorama, we see very dark material under us, an illuminated cliff, and then the sky. The point being,
if Philae gets ejected because of outburst, then will it wake up and then take pictures again?
That's always possible. I mean, we're in a very shaded spot. I mean, one of the ironies is that, in fact, if we had landed on the surface, we calculated that by March this year, we would have got too hot for the electronics on the inside. And by actually being in the shade, we're pretty cold soaking, mind you. That's one of the big worries. We've been in cold soak for a long time. The electronics may be fried or inverse fried, unfried, if you like, chilled. So we don't really know. But if it does come back to life, we may be there at a more active phase. So this business of will it get ejected if there's activity locally, it's always possible. But it's very tenuous. If you think about the ejected material from comets, it's actually about the same density as the Earth's atmosphere 100 kilometers up. So it's just not like a strong wind or anything like that, right? There's very little force from the... We see it on the solar panels. We actually, when we're close in, we actually feel the wind blowing us and moving us around. We are able to sense that.
Okay. Okay, Mark, thanks for this brilliant talk. And my question is, you showed in the last image this jet that came up, 3-second thing. So what's the origin of that jet?
Well, it's just not really understood. I mean, this is a fairly wide field image taken from a distance. It may be that there's a promontory which just moved into sunlight as it tipped, as the base of the comet tipped into sunlight there. Nobody knows yet. It's being looked at. But we expect to start seeing very transient effects. We know that comets, of course, occasionally just go through big outbursts.
Jets everywhere in the universe.
There are jets everywhere, exactly. Yeah, indeed. We take this one? No, you've got the mic, yeah.
So your best case and scariest scenario is that the comet breaks in half. If that happens, have you modeled what's likely to occur? Is there risk to the spacecraft?
It's an interesting one. People actually think it may not fall apart under centrifugal force, which you would think it may actually slump and fall together. It's all going to be very slow. The centrifugal force is roughly the same as the gravity, so there's not going to be any kind of, balls on the end of a string. You cut the string and they fly off into space. It's going to be a slow motion activity at best. And at the moment, at least, we're 100, 200 kilometers away routinely. We have an issue at the moment, interestingly, that in order to maintain our orientation as we fly through our hyperbolic flybys, well, always we use star trackers on board. We recognize constellations on the sky, compare them to a catalog on board. And as we fly through the comet's coma now, we see dust particles everywhere, and we're seeing too many of those, and we're confusing them with stars, and we're not able at the moment to fly that close to the comet. So we're still looking at this. If you know any people that have got 10 years old assembler code expertise on star trackers, somebody here, right? It's an issue. We'd actually are looking to how we might be able to reprogram the star trackers. It's very difficult to do at that distance.
For the Mars rover. Yeah. What scientific questions do you hope to answer in the remainder of the mission?
Well, I think there's this issue of overall composition, particularly of organics. This discussion about amino acids, for example. We know that on previous comets that glycine has been seen, but glycine's an interesting amino acid because it's the only one that's not handed, okay? It's not chiral. The crucial thing is all life on Earth is one-handedness. And if we go and we see that comets are all that handedness in their amino acids as well, that's an interesting thing. It's unlikely to be the case. It has to do with how life evolved on the Earth and picked one-handedness over the other. But if there's a slight predominance of one-handedness over the other in the comets, that would be very interesting. It's really to study the comet's evolution over time, okay, to try to understand the amount of wastage, the amount of erosion that happens during one perihelion passage. What are the structures? How does the outgassing occur? Where does it come from? Trying to understand how comets are put together by effectively see them fall apart, if you like. And we've never been able to do that before. We've never been able to fly with a comet over an extended period and see the before and after changes. And we'll watch it as it cools down as well, of course. As we come out from the sun after August, we'll see how some of those processes reverse and how the dust settles back down on the surface. So in that sense, it's not kind of the high-end questions, are we made of comet stuff? But for scientists, this is exactly what we love to do, right? Go out and investigate weird and wonderful objects, take them apart, and tell our friends about it.
Thank you.
Thank you very much.